Trigonometric substitutions. In this section, we're going to take a look at integrals where a certain expression in the integrand leads us to make a certain substitution involving trigonometric functions. And then we'll see what happens as a result of that substitution. So, unfortunately, with this section, you sort of do need to memorize something. If we see an integrand that has these certain expressions in them, the square root of a squared minus x squared, the square root of a squared plus x squared, or the square root of x squared minus a squared, we need to make certain substitutions to simplify the integrand. So if it's the square root of a squared minus x squared, we make the substitution, we let x equal a sine theta, where theta falls between negative pi over 2 and pi over 2. And then we're going to need to use a certain identity. And it ends up being a Pythagorean identity. 1 minus sine square theta is cosine square theta. Similarly, if we have the square root of a squared plus x squared, we use the substitution x equals a tangent theta. And then we'll use the fact that 1 plus tangent square theta is secant square theta. And finally, if we have the square root of x squared minus a squared, we'll make the substitution x equals a secant theta, and then we'll use the identity that secant square theta minus 1 is tangent square theta. Now, to give you an idea of why we might make that substitution, let's consider that first case. So, if we had the square root of a squared minus x squared, and I make the substitution, if I let x equal a sine theta, then what happens here in the integrand, or in that radical, is I would then have the square root of a squared minus, now x squared would then become a squared sine square theta. I can use a little bit of factoring and write that as the square root of a squared times 1 minus sine square theta. Now 1 minus sine square theta is cosine square theta. And now the square root of, well, notice that both of those are perfect square factors. This becomes a cosine theta. Now, we really should be more careful. We should say, well, shouldn't there be absolute values about that? When you take the square root of a square, we really should have absolute values. But since we've made the substitution, negative pi over 2 is less than or equal to theta is less than or equal to pi over 2. Since we've made that stipulation on the substitution, remember that on negative pi over 2 to pi over 2, that cosine theta is greater than 0 when theta is between negative pi over 2 and pi over 2. And we usually make the assumption that a is positive as well. And so we really don't need these absolute value bars, and I won't be concerned with them on these integrals. Alright, so let's see an example. We are asked to evaluate the integral of x cubed over the square root of x squared plus 4 dx. Alright, so since I see this of the form, since I see that square root of x squared plus 4, well, that's x squared plus 2 squared. So I'm going to make the substitution. I'm going to let x be equal to 2 tangent theta. If x is equal to 2 tangent theta, and while I'm here, let's kind of just find the differential, because I'm going to need to get rid of that dx. If x is 2 tangent theta, then dx would be 2 secant square theta d theta. Alright, now the square root of x squared plus 4, that would then become the square root of 4 tangent square theta plus 4, which is the square root of 4 times tangent square theta plus 1, which is the square root of 4 times secant square theta. And so then that becomes 2 secant theta. And this is going to simplify the integral for us. Alright, so then after all these substitutions, this becomes the integral. All right, so x cubed. X was 2 tangent theta, so that's going to be 2 tangent theta cubed. The square root of x squared plus 4 is 2 secant theta. The dx is 2 secant square theta d theta. And now this looks worse, but let's see what happens. All right, so let's see. This becomes then the integral of 2 cubed, that's 8 tangent cube theta over 2 secant theta times 2 secant square theta d theta. So notice now I can do some reducing. I got an 8, and these 2's reduce out. These 2's reduce out. I have a secant theta in the denominator, and I have a secant square theta in the numerator. So this secant theta divides out with this secant theta. And so then this becomes more simply the integral, or 8 times the integral of tangent cube theta secant theta d theta. All right, so now, remembering what we've learned in the previous section, since I have an odd power on the tangent, I'm going to rewrite this as 8 times the integral of, let's see, we're going to have a tangent square theta times a tangent theta secant theta d theta. And I'll make the substitution now. If I let u equal secant theta, then du is equal to secant theta tangent theta d theta. And I'll also remember that I can replace that tangent square theta with a 1 plus secant square theta. So then this becomes 8 times the integral of 1 plus u squared du. So then we get 8 times, no longer an integral, we can evaluate this integral easily. Let's see, we'd have 8 times u plus 1/3 u cubed plus a constant. So then this is 8u. Now u was secant theta. 8 secant theta plus 8/3 secant cube theta plus a constant. But now our original integral was in terms of x, so we need to get rid of thetas and replace this with something in terms of x. All right, so here's where we have to use our knowledge of a little bit of trigonometry. If x, so going back, if x was equal to 2 tangent theta, then x over 2 was equal to tangent theta. And so now I'm going to draw a little triangle. If there's my theta, then the tangent of that theta is x over 2. And so I would put an x here and a 2 here, opposite over adjacent. And then the Pythagorean theorem tells me that the hypotenuse would be the square root of x squared plus 4, which should look familiar. Right? We had that square root of x squared plus 4. So then from this triangle, then secant theta, the secant theta is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so the secant is hypotenuse over adjacent. So then secant theta would be the square root of x squared plus 4 over 2. And so then this becomes, our integral becomes 8 times the square root of x squared plus 4 over 2 plus 8/3 of the square root of x squared plus 4 over 2 cubed plus a constant. And then if we simplify this a little bit, we would have 4 times the square root of x squared plus 4. And now let's see, the square root of x squared plus 4 cubed over 2 cubed, well, the 2 cubed is going to be an 8, and so those 8s are going to reduce out, so we'd have plus 1/3, and I'm just going to write x squared plus 4 to the 3/2 plus a constant. All right, so there's an example of how we can use this trigonometric substitution. Let's consider the example, integral of dt over t squared times the square root of t squared minus 16. This would be a good one to try out on your own, so now would be a good time to pause. All right, I see this expression involving the square root of t squared minus 16, so that's t squared minus 4 squared. All right, so I'm going to make the substitution. I'm going to let t equal 4 secant theta. Then dt would be 4 secant theta tangent theta d theta. Now, while I'm at it, let me simplify that square root of t squared minus 16. So the square root of t squared minus 16 would become the square root of 16 secant square theta minus 16. That would be the square root of 16 by secant square theta minus 1. And so that would be the square root of 16 tangent square theta using a Pythagorean identity. And so that would be 4 tangent theta. Also notice, and later on we might need that triangle that we saw in the previous exercise. So notice then that secant theta is t over 4. So I can build a triangle out of that. If secant theta is t over 4, then I would put t and 4. And the remaining side of the triangle is the square root of t squared minus 16. All right, so let's keep all that in mind, and let's rewrite our integral. Let's see, dt is 4 secant theta tangent theta d theta, and the square, let's see, t squared, that would be 16 secant square theta times the square root of t squared minus 16 ends up being 4 tangent theta. So let's see, after we do all of our reduction, let's see, what can we remove? We can remove the 4s, I can remove a tangent theta, and I can remove a secant theta. So then this becomes 1/16 integral of 1 over secant theta d theta. Oh, we haven't seen one like this before. But wait a second, from trigonometry, 1 over secant theta, the reciprocal of secant theta is just cosine theta. And the integral of cosine theta is sine theta, and then plus a constant. All right, so now going back, we need to substitute back to put this in terms of t. So sine theta, going to our triangle, sine theta is opposite over hypotenuse. And so then this becomes 1/16 times square root of t squared minus 16 over t plus a constant. All right, how about the integral of 1 over the square root of 9 minus 16x squared dx? Well, this one doesn't fit the pattern perfectly. So what we need to do here is rewrite it so it does fit the pattern. So what I'm going to do is first, I'm going to do some factoring. Let's work in that radical. I'm going to factor out 16. So I've got a 16 times 9/16 minus x squared. See, now if I look at that, that looks nicer. Because now I can say, well, that's, don't forget the dx, because now that's the same thing as the integral of 1 over 4 times the square root of 9/16 minus x squared. And now that fits a pattern. All right, so then that becomes the integral, that becomes 1/4 of the integral of 1 over the square root of 9/16 minus x squared dx. And now I see this, I notice that 9/16 is a perfect square. And so now from here, I can make the substitution. I can let x equal 3/4 sine theta. And so then dx would be 3/4 cosine theta. And the square root of 9/16 minus x squared, after a little bit of work, that square root of 9/16 minus x squared, that becomes 3/4 cosine theta. So this integral becomes 1/4 integral of 1 over 3/4 cosine theta times, and I forgot my dx should be 3/4 cosine theta d theta. So that would be times 3/4 cosine theta d theta. And so now look at what I've got. What can I remove? I've got these 3/4, they go away. I've got this cosine theta, they go away. And so then this just becomes 1/4 the integral of d theta. And so then that's 1/4 theta plus a constant. All right, well, now I've just got to get this back in terms of x. Well, I need to solve, I just need theta. This doesn't have any sines or cosines or any trigonometric functions attached to it. So if I go back to the fact that x is equal to 3/4 sine theta, then multiplying through by 4/3, I'd have 4x over 3 is sine theta, and then theta would be sine inverse of 4x over 3. And so then the integral becomes 1/4 sine inverse 4x over 3 plus a constant. So this integral ended up just being a sine inverse. We actually could have done this integral back in the previous chapter. So let's look at this integral again. From this, no, not this point. Let's look at that integral again from here. We had 1/4 integral of 1 over the square root of 9/16 minus x squared dx. We learned back in the previous chapter that if we have the integral of 1 over the square root of a squared minus x squared, that was with a dx, that was sine inverse of x over a plus a constant. In fact, that was one of the ones you're supposed to have memorized. And so now the a is just 3/4. So from that point, we could have gone straight with this formula and written that this is 1/4 times sine inverse of x over 3/4 plus the constant, which again becomes 1/4 arcsine of 4x over 3 plus the constant. All right, so either approach is correct, but notice how if you forgot that formula, you could use the trigonometric substitution to evaluate the integral. Of course, if you remember the formula, it's a lot easier. All right, let's consider one more. Here we're asked to evaluate the integral of dx over the square root of x squared minus 6x plus 13. Now, if we look at this, we say, well, gosh, this doesn't look like anything that we've seen. It doesn't fit any of the forms. So we're going to make it fit the form, okay, by using other techniques. So x squared minus 6x plus 13, I'm going to complete the square. X squared minus 6x plus 13 is the same as x squared minus 6x. Now completing the square on the x squared minus 6x, that would be x squared minus 6x plus 9. Let me use a different color here. So plus 9. Now wait a second, I still have this plus 13, but now to keep it even, I've got to subtract 9. And so this then can be written as x minus 3 squared plus 4. So, there's some side work. This becomes integral dx over square root of x minus 3 squared plus 4. So now I'm going to make the substitution. Now, it's not an x squared plus 4, it's an x minus 3 squared plus 4, but I can make the same substitution that I would. I'm going to use, let x, instead of x, I'm going to make it x minus 3. Let x minus 3 equal 2 tangent theta. Then dx is would be 2 secant square theta. And that square root of x minus 3 squared plus 4, after a little bit of work, that would end up being the square root of 4 secant square theta, and so that becomes 2 secant theta. So then this integral becomes 2 secant square theta, there should be a d theta there, 2 secant square theta d theta over 2 secant theta. We can get rid of the 2's, and we can get rid of a secant, and so we now have the integral of secant theta d theta, which, from memory, is natural log absolute secant theta plus tangent theta plus a constant. All right, now we got to get this back in terms of x, so we got to get rid of that secant theta and that tangent theta, so we have to talk about what is the theta. All right, so x minus 3, if x minus 3 is 2 tangent theta, then x minus 3 over 2 is tangent theta. There's my theta, so x minus 3 over 2. And with a little bit of work, we can find that then this side of the triangle is the square root of x minus 3 squared plus 4. Amazing, isn't that? So then the secant of theta would be, so then this becomes natural log absolute. Secant theta would be the square root of x minus 3 squared plus 4 over 2. And the tangent of theta would be x minus 3 over 2 plus a constant. Now, notice that these have a common denominator, so are inside the absolute, so I can write them as a single fraction. Natural log absolute square root of x minus 3 squared plus 4 plus x minus 3 over 2 plus a constant. And I can take this just a little bit further. Remember from our properties of logarithms, if I have the logarithm of a quotient, I can write that as a difference of logarithms. And so I can write this then as the natural log of the square root of x minus 3 squared plus 4 plus x minus 3 minus the natural log of 2 plus a constant. And now what happens is, if we look at the answers in the back of a book or something, since the natural log of 2 is a constant, it gets grouped together with that other constant from integration, and we just call this plus some other constant. Usually, we call it C1 or C something else. All right, so that's something that happens in these types of expressions. All right, so there's some examples of how we can use trigonometric substitutions to evaluate integrals, and that completes the section.